Hey everyone, welcome back to Trigonometry. This will be lecture 14 of the course, and in this section we're going to discuss something called the law of sines. So let's go ahead and jump into it. And so we'll call this section 3.6 the law of sines. And so we've discussed in the past solving triangles. And we specifically looked at how to solve triangles that involved a right triangle. So we have seen how we can solve triangles that have a right angle. So what we want to talk about in this case is we're going to try to figure out how to solve triangles that don't necessarily have a right angle. So what about oblique triangles? So an oblique triangle is a triangle that doesn't have a right angle. They generally come in two varieties. You've got this one here, this kind of thing here. And just to kind of point this out, the labeling convention is that you label the angles with the capital letter and then the opposite side with the corresponding lowercase letter. So you got an ABC triangle, you'd label it like this. And this is an oblique triangle where all of the angles are acute angles. So this triangle has all acute angles. Right, acute angles meaning less than 90 degrees. This might be 60, 60, 60, for example. Okay, something like that. The other option would be when you have triangles that look more like this. They're maybe got a more stretched out appearance. Right, so this angle in particular is an obtuse angle. Okay, and so this triangle has an obtuse angle. Okay, and these are the two varieties, right? So this would be, maybe you could label this A, B, little b, C, little c. Okay, so both of these are what we would call oblique triangles because they're not right triangles, but they can come in different varieties. You can have the case where all of the angles are acute, or you can have the case where where one of the angles is obtuse, one and only one. You can't have two obtuse angles, otherwise your triangle would not be a triangle, or it would exceed 180 degrees. Okay, so let's state the law of sines then. So the law of sines. Right, and the law of sines is going to be the tool we're going to use to solve triangles like these. Okay, it's going to be one of the tools anyways. So the law of sines says, given a triangle with sides ABC, opposite angles ABC respectively. Okay, given a triangle with sides ABC, opposite angles ABC respectively, the following relationship holds. The following relationship holds. And what we say is that, so just to draw the triangle, just to be clear, you've got an A, B, B, C, C. So what this law of sine says is that side A divided by sine of angle A is equal to side B divided by sine of angle B, which is in turn equal to side C divided by sine of angle C. Okay, so this is the relationship. And so when you first look at this, it may not be obvious why such a relationship should be true. We can prove this. The proof, I'll call it a proof. The proof or demonstration is very simple and straightforward. So let's go ahead and run through the proof. Okay, so let's run through the proof and talk about why this works. So what we're going to do is we're going to start by just drawing a nice triangle here. You know, this will be the acute version of the proof. You can do something similar with the obtuse version of the proof. But so I'm going to label a triangle here, A, B, B, C, and then down here I'm actually going to kind of just go like this because I'm going to end up doing something funny here. All right, so this is the same as saying the side is C, but I just kind of moved it off. What we're going to do is we're going to drop a perpendicular from C down to the line AB, and that means these are right angles. Okay, so we're going to drop a perpendicular from C down to line AB. Okay, and we're going to denote the length of that perpendicular that we dropped as h. You can think of that as the height of the triangle if you like. Okay. Now there are two triangles defined now. Okay, and let's label this point D down here where the perpendicular intersected AB. Okay. So you've got the triangle ACD, right? So that's ACD, so this side over here. Okay, kind of think of this as one side. And the other side, of course, is BCD. Right? So you can think of this as the other side. So you got these two triangles. Okay? And using these two triangles, we're going to quickly develop two of the three ratios. Right? And so just using the definitions, from right triangle trigonometry, we have, what do we have? Well, we have that the sine of B is equal to, well, this is B, so the sine, remember, is opposite over hypotenuse, so it'd be h over a. Okay, and then the sine of A, we can do something similar. The sine of A is going to again be opposite over hypotenuse, so it's h over b. Okay. And we can use these. We can do some algebra to see that h here is equal to a times the sine of b, and h over here is equal to b times the sine of a. Okay, very nice. And so I've got two expressions for h. I've got two equations, both of them solved for h, so I can equate these two, right? So this is going to imply that a sine of b is equal to b sine of a. Okay. All right, and so I can easily do a little algebra here, and I'm pretty much at the finish line, right? So I can divide both sides by sine of a, for example, and I have a sine of b over sine of a equals b. Like I've got this one, I can divide both sides by sine of b as well, and I get a over sine of a equals b over sine of b, which is exactly what is stated in the law of sines, right? So we've got this this relationship established for two of the three sides slash angles. All we would have to do to pull 3 into this would be to, instead of, all right, let's redraw this. I've got my A and my A, my B and my B, C and C. What I could do is I could drop my perpendicular from B down onto AC instead. Right before I came from C down, but I could just as well do it like this and call that H. Then I could set up a similar scenario with sine of A equals h over c, and sine of c equals h over a, right? And I would just do the exact same, I could do the exact same thing. So the same derivation could be done for side C and angle C. Okay, and so you can see how you could do this. Okay, so this is the law of sines, and this is why the law of sines works. Okay, and so let's take a look at an example of how to use this. Okay, let's solve the triangle. Oops. Solve the triangle. Okay, and I'll just draw the triangle. Normally they don't draw them for you, but that's okay. We can just draw them quick. And so I've got my A, B, B, C, C. And I know some things. I know that this is 46 degrees, and maybe I know that this is 65 degrees, and maybe I'm told that C is equal to 56. Okay, so I've got this triangle that I want to solve. Well, probably the best place to start is by finding the angle B. So let's find B to start with, angle B. That's the easiest thing anyway, so we say that B is definitely 180 degrees minus these two. So the whole triangle is 180 degrees, and I can subtract off 46, and I can subtract off 65. And what do I get? Well, when I do that arithmetic, I get 71 degrees. Okay, so I know B is 71 degrees. Okay. The next thing I can do is maybe I could try to find A. Sorry, little a, not big A. Let's find little a. All right, let's find this side here. Well, I know that I'm going to need A over sine of A. Now, if I do B over sine of B, I know sine of B, but I don't know little b, so that's not super helpful. So instead I'm going to do C over sine of C. I'm going to use this setup. Okay, and so then I plug in my numbers, and I get A over sine of 46 degrees is equal to 56, which is C, over sine of 65 degrees. Okay, and so I can easily figure out what A is. I can do a little cross multiply and divide, or I could just do a little algebra and say A is equal to 56 times the sine of 46 degrees divided by the sine of 65 degrees. All right, something like this. Okay, and when I do that, I would get 45.2, thereabout. I think technically this is a 3, so just be careful. This is supposed to be sine of 63. You might get different answers. Yes, definitely. So be careful there. My handwriting was a little sloppy, so sine of 63 degrees. So this is 63 degrees, and that's going to make this 71. Okay, and so you get 45.2. And we could find B next. So I can use, again, I can use A over sine of A equals B over sine of B. Okay, and so if I need B, then I would say B is equal to A times the sine of B over the sine of A, and I better plug those quantities in. So B is equal to A, which we just found to be 45.2. Times the sine of B, which we found appeared to be 71 degrees, divided by the sine of A, which is 46 degrees, right? And so you can figure that one out yourself. Okay? So that's an example of how to use the law of sines to solve a triangle, so we can get all three pieces. Okay, very good. So admittedly, that was kind of the easy case. That was kind of an easier example. Okay. Okay, so sometimes the examples can be more challenging. So sometimes the given information may imply the existence of a second valid triangle. Okay, and so an example of that might be, let's say I have a triangle. Well, let's say I'm told this side here, right? We'll say it's, oh, actually I'm not told this side, sorry. Let's say I'm told this side here. I'm given side B. Okay, and I know angle A. I don't know the length of this side C, but I'm told the length of side A, which is this guy. But if I don't know what this side is, and I don't know what these other two angles are, it may be possible that A could look like that or like this. Right, so in this scenario, there are two possible triangles. Right, so I've got this triangle here, right, where this is my B, this is my A, and this is my C. But I've also got this triangle here, this kind of bigger triangle. Okay, remember, I know nothing about this angle. This is unknown. And I don't know anything about this angle. And I don't know C. Right? All I know is little a, big A, and B. I know two sides, I know two adjacent sides, and an opposite angle. Okay? And so this kind of scenario is what we kind of think of as the hard case of the law of sines. So this is the hard case. Okay, let's do an example of this hard case and just see what kind of shakes out when we look at this. Let's do an example like this. Okay, so let's consider this triangle. Consider a triangle A equals 40 degrees, little a is 54, and B is 62. Okay, so we know the ratio A over sine of A. We can see that both of those are given. So let's use this to find angle B. Okay, so let's find B. Okay, so we're going to find B. So we're going to go A over sine of A equals B over sine of B. Okay, we can plug those values in, so I get 54 over sine of 40 equals 62 over sine of B. Okay, and so I can do a little algebra to this, and what you'll find is that the sine of B is equal to 62 times the sine of 40 over 54. Right, so that's just algebra. I'm just taking this expression here, rearranging it. Okay, and so you can figure out what this is equal to. This whole thing here, sine of B, is equal to something approximately 0.738. Okay, and if you plug this into a calculator, if you go like this, B is equal to the inverse sine of 0.738, what the calculator will typically spit out is one of the two possible angles. And so the first one it'll spit out usually would be 48 degrees or 47.5 degrees. It'll spit this one out. Okay, but there's a second possible angle. There's a second angle that satisfies this also. Right, and the way you can kind of think about that is if I have, let's take, the upper half of the unit circle here. Okay, and so here's my x-axis. And so I found the 48 degrees, and it's going to be like right about, you know, little like bit like that, right? So I've got 48 degrees. And so what that's telling me is that this length here is 0.738. Okay. Oh, sorry, that's the cosine. Not that length. This length is 0.738. We're talking about the sine, right? So the vertical length here. And so there's another angle that works for the sine as well. Actually, it's over here, right? So this is also 0.738, isn't it? And what angle is that? If I start over here and I go all the way around, well, it's like 180 minus 48, and you find that that's 132 degrees. Okay. So the triangle, well, so what this all amounts to is that the angle B can be either 48 degrees or 132 degrees. We don't know which yet, and in fact, there's no way to tell which. There's not enough information given in the problem to pin down one or the other. Okay? And so we actually end up having two separate triangles. So the first one looks like this, kind of like the picture we drew earlier, where I know that this is B and it's 63. Okay, I've found A just, sorry, I'm given A is 54. And I'm given 40 degrees here. Okay, and then this angle here is the 132 degrees. Okay. And the other possibility, so this is triangle 1. The other possibility is that the triangle looks like this. I've again got my 40 degrees here. This is my A. And this is C up here. I should probably put those on there. I'm told B is equal to 63, and I'm told that A is equal to 54. I don't know C yet, and I don't know angle B. Well, sorry, I do know angle B is 48 degrees, sorry. Yeah, so from right here. All right, so this is triangle 2. Okay. And so in each of these cases, either of these triangles are possible. Both are possible. And so it could be either one. We don't know which one. Okay, so when that happens, we basically got to figure them both out. Okay, and so I'm going to call this one over here C1, and I'll call this C2. And angle C1 and C2 will be different as well. Right, so this will be C2 and this will be C1. And other than that, though, so I, depending on what I choose for these, which one I'm working with, I can find both just fine using the law of sines, but they're different triangles clearly, right? So let's finish this triangle up first. Let's find C1. Okay. So C1 is equal to 180 degrees minus 40 minus 48. Okay, and when I do that, what do I get? I get 92 degrees. Okay, so that means up here I've got 92 degrees. Okay, let's find C2 while we're at it. So it's 180 degrees minus 40 degrees minus 132 degrees. And that one is very small. It's 8 degrees. So that makes sense. This is 8 degrees, very small angle. Okay. Now what I don't have yet is C1 and C2. Let's find big C1. Okay, so C1. What I'm going to do is I'm going to use law of sines here. So C1 over sine of C1 equals A over the sine of A. Okay, and so I can just plug those quantities in. I'm looking for C1. Again, I'm referencing this triangle here. So that's C1 over the sine of 92 degrees, and that's equal to 54 over the sine of 40 degrees. Okay, and so that means, well, I'll just tell you the answer here. You can do the algebra, but it's 54 times sine of 92. So that implies that C1 is equal to 84. So here I've got an 84. Okay. And finally, we can find C2. So again, we'll use C2 over sine of C2 equals A over sine of A. And so I can plug everything in. I get C2 over the sine of 8 degrees equals 54 over the sine of 40 degrees. So C2 is equal to, you can do the algebra here again, it's just it's basically the same as the one above it. You can do it. And what you'll find is, in this case, C2 is equal to 11.7. And that makes sense. It's a smaller leg here, right? Okay. And so this is an example where the information given actually implies the existence of two possible triangles, not just one. Okay? And so in that scenario, you really have to do both of them. Okay? You really have to do both of them. Okay. All right. Okay, let's do another example that's kind of like this, but has a slightly different twist to it. Right, so you always have to be very careful with these, that you're considering all of the possibilities. So let's consider the triangle consider the triangle ABC. Okay, and so we want to solve this thing. Let me write this out. Okay, well, this is kind of what it would look like, we think, anyways. So I've got my A down here, and I'm given that angle is 43 degrees. I know the little a across the way is 81, and I'm told that B is equal to 62. Okay. Okay. So for this example, we know a ratio, right? We've got a whole ratio. So in the previous example, let me think here. Let me look. Yeah, in the previous example, we knew a ratio too. So let's go ahead and use this ratio to find B. So we're going to use A over sine of A equals B over sine of B. And so when we plug these quantities in, we get 81 over sine of 43 degrees equals, so remember this is B over here, and I'll just put C, right? So 81 over sine of 43 equals 62 over sine of B. Okay. All right, and we can do some algebra to this, and we'll see that the sine of B is equal to 62 sine of 43 degrees divided by 81. And so we'll see then that the sine of B is equal to 0.522. So a little better than a half, right? And that's going to imply that B is equal to the inverse sine of 0.522. All right, so, but here again, you know, if you plug this just into your calculator, you're going to get 31 degrees. But here again, you have to be careful because there's actually two possibilities, right? So if this is my unit circle, then here's my first one. This is 31 degrees, right? And that's telling me that this height here is 0.522. Right, but you can clearly see that there would be something over here as well that's 0.522, right? And that angle goes all the way around and would be 180 minus 31, so I believe that's 149 degrees. Right, so There are two options for B. There are two options for B. It could be 31 degrees or 149 degrees. Okay. So the given angle, here's kind of the nice thing about this one, though. We're given the angle A is equal to 43. We're told that A is equal to 43 degrees. And so if we compare that with what we just calculated, what do we get? Well, for an angle C, right? So for C, we know that C is equal to 180 degrees minus angle A is given as 43 degrees. Sorry about that, minus 43 degrees. And then one of our options for B is 31 degrees. And so when we plug this whole thing in here, we get 74. So 180 minus 74, which is, what is it? Shoot, I didn't write that one down. So we would get, 180 minus 43 minus 31, so we get 106 degrees. Okay, so that's one option. What if I plug in the other angle, 180 degrees minus 43 degrees minus, what was the other option for B? 149 degrees. Well, if I do that, I'm going to get something kind of wacky, aren't I? If I go 180 minus 43 minus 149, what do I get? I get negative 12 degrees. That's a problem, right? The sum of the legs of the triangle have to equal 180 degrees, and none of the angles can be negative. We're talking about a triangle here. And so what that means is that the 149 is not valid, right? This means that 149 degrees is not a valid triangle, right? So there really is only one option. There really is only one option, and that's where B is equal to 31 degrees. Okay, so let's regroup here. What were we given? We were given 43 degrees. We were given B equals 62. We were told A is equal to 81. And we didn't know the rest of it, but now we know that B is equal to 31 degrees. Okay. We know that B must be equal to 31 degrees, and then we've kind of inadvertently calculated C here is 106 degrees, right? So the other triangle where, where we were looking at a potential 149 degrees here would have made the triangle invalid. Okay, so there's only one valid triangle. So in this example, there is only one valid triangle. Right, it kind of looked like there were two possibilities for a second, but it turns out there was really only one. Okay, and so can we find the angles or the side C? Of course. We'll just use C over sine of C equals A over sine of A. And we get C over sine of 106 degrees equals 81 over sine of 43 degrees. Okay, so that means C must be 81 times the sine of 106 degrees over the sine of 43 degrees. And so that means it's 114.2 right, when you do the calculation there. Okay, and so that is what we need to do for this lecture. So that's the law of sines, folks. So that's one of two extremely powerful tools that we can use to find all of the sides and angles of a triangle. Okay, so that's the law of sines. Okay, and I think we'll end this lecture with that example, and then next time we'll get into the law of cosines, and then we'll practice using them together to solve problems. Okay, so we'll leave it here until the next lecture. Take care.